Hello, I am Judit Moschkovich, Professor of Math Education at UC Santa Cruz. I am talking to you from Santa Cruz, California, unceded territory of the Amamutsun. In this presentation, I will first summarize a theoretical framework that is a sociocultural approach to academic literacy in mathematics. And then second, I will use a classroom example to illustrate that framework and make recommendations for instruction to support English learners in mathematics classrooms. Articles with that example and other articles mentioned at the end will be available in the resource room. So this framework shifts from a simple view of mathematical language as single words to a complex view of both language and mathematics. This framework also assumes that mathematical thinking and learning involve language. And what I propose in this framework, it's in an article that appeared in 2015, is that there are three intertwined components to academic literacy in mathematics: mathematical proficiency, mathematical practices, and math discourses. And you see this is an image of how they're integrated, they happen simultaneously, they're sort of organically working together, so that language demands and mathematical demands happen simultaneously, not separately, but they're intertwined. This framework can be used to analyze student activity, it can be used to design tasks, and most importantly for the talk today, it can be used to plan lessons to support English learners. A few framing sociocultural assumptions. One would be that math activity includes practices and discourses, not only individual knowledge. Another one would be that mathematical activity is mediated by language, representations, and social interaction. The next one is that discourse is central to participating in and appropriating mathematical practices. Lastly, but perhaps most importantly, a sociocultural framing means that the focus is on the potential for progress in what learners say or do, not on learner deficiencies or misconceptions or deficits. So to give you a sense of what ALM, I'll just say that's short for academic literacy in mathematics, what it's not only about reading word problems, but let's take a look at a word problem as an example. First of all, I'm going to read the word problem. A boat in a river with a current of 3 miles per hour can travel 16 miles downstream in the same amount of time. It can go 10 miles upstream. Find the speed of the boat in still water. So what academic literacy in mathematics is not, it's not about using keywords to write an equation. There's no keyword here that tells you what to do: add, subtract, divide. It is not about extracting the numbers and writing an equation, because again, there's much more that needs to happen before I can do that. Most importantly, it's not about textbook definitions. Textbook definitions are not going to help us in making sense of this problem. And it's not about learning math vocabulary or technical vocabulary. If you actually read this problem, the crucial vocabulary are things like downstream, upstream, and my favorite one is in still water. I always want to know, how do they know what the speed of the boat is in still water? Do they pick up the boat from the river and put it in a lake where it's still? In any case, that's the crucial vocabulary. So if academic literacy in mathematics is not vocabulary, then what is it? So again, just to highlight those two words in one phrase, those are the crucial vocabulary pieces. Academic literacy in mathematics involves concepts. You need to understand rate. You need to understand the difference between extensive quantities like miles and intensive quantities like miles per hour. So it involves understanding concepts. That's the math proficiency part. It also involves math practices. One of our favorite ones, make sense of the problem, comes from the Common Core. Making sense of the problem is a big math practice. One important way to make sense of problems is to represent them. So drawing a picture of this might be really useful. And then the third component is math discourse. You might have noticed how long that first sentence goes on for. A boat in a river with a current of 3 miles per hour. And it continues. Those are called either nested or subordinate clauses, and they're typical of mathematical discourse, particularly for word problems. So What academic literacy in mathematics is math proficiency, particularly CU is for conceptual understanding, practices and discourse, and those three components work together simultaneously. For a definition of math proficiency, I'm going to use the 5 strands, again, listed there from the National Research Council adding it up, conceptual understanding especially. Procedural fluency is what people typically think fluency in mathematics is calculation. I'm not even going to talk about that because conceptual understanding is much more important. Reasoning. And then for strategic competence, one of the definition of that is competence in formulating, representing, and solving mathematical problems. Novel problems, not exercises that are just calculating. The way I summarize those is understanding, reasoning, and representing. For math practices, what are those? Well, they're using language and other symbol systems to think, talk, and participate in the practices that are the objective of school learning. Now, there isn't one single set of math practices or one mathematical community, and those practices vary across communities. We've got mathematicians, statisticians might do different practices, a traditional classroom where the mathematical practices are actually using worksheets, and a reform classroom where students are actually making sense of problems. So there are common practices labeled academic mathematical practices. My favorite ones, I've collected a list from my own research and other people's research: problem solving, sense making, reasoning, modeling, looking for patterns, structure, or regularity. That comes straight from the Common Core. But I don't want to forget abstracting and generalizing. Generalizing is fundamental to algebraic thinking. Using and connecting mathematical representations. The National Council of Teachers of Mathematics, again, always focuses on connecting multiple representations. And lastly, imagining, because many of the things that we're talking about, infinity or zero, are things that we're imagining. So again, that's just an incomplete list of some of the valued mathematical practices. What about mathematical discourse? One way to think about it is that many of those valued academic mathematical practices involve mathematical discourse. I'm just going to read this quote. As students develop academic literacy in mathematics, they're learning to communicate mathematically by making conjectures, presenting explanations, and constructing arguments that involve mathematical objects with mathematical content and towards a mathematical point. Now, the important thing about math discourses is that the framework goes beyond low-level language skills, beyond just vocabulary. So this is about communicating using conjectures, explanations, and arguments. Also, mathematical discourses are multimodal. That means that they include more than one mode: listening, talking, reading, writing, and gesturing, and multiple sign systems. Another important thing about mathematical discourse is that they are not about static dictionary definitions, but multiple meanings for words are situated. They're dynamic and negotiated. And lastly, students and teachers use multiple resources, everyday and formal registers in home language. So again, classroom mathematical discourse involves both everyday and formal math registers, and it can include more than one language. So why label this mathematical discourses? The shift from language to discourses is mostly because there's a problem with the word language. There's multiple meanings. Language can mean vocabulary or formal math vocabulary. It can mean discussions. It can mean talk, writing. It can mean reading word problems. It can mean home language, everyday language. Academic language, in many instances in teaching, can be reduced to single words, vocabulary, or grammar. So a more complex view of mathematical language is not only a specialized vocabulary with precise meanings, but instead the competence to communicate about mathematical concepts, and most importantly, to participate in mathematical practices. So if students are participating in academic literacy in mathematics, we can see and hear them actively using conceptual understanding, actual concepts, not just calculation, and participating in mathematical practices, many of which are discursive. So to illustrate that framework, I'm going to use a classroom example, and I'll make 2 recommendations for instruction to support English learners in math classrooms. Let me tell you a little bit about the example. It comes from a third grade classroom, bilingual, urban in California in the United States. There were 33 students at the time. They were labeled as limited English proficiency. Those labels have changed and they're no longer used. The lesson the teacher explained was English as a second language math lesson where students were going to use English to describe quadrilaterals using paper shapes. So typically the teacher is bilingual. Just this day, they're going to be speaking only in English. In general, the teacher introduced students to topics in Spanish and later conducted lessons in English. They'd been working on a unit on 2-dimensional geometric figures, and for several weeks, they had been discussing and using words as radius, diameter, congruent, and so on. And particularly for this little video clip, the names of different quadrilaterals in both Spanish and English. They'd been talking about shapes. The teacher had asked them to point, touch, and identify different shapes. So again, this is one where students were also had in front of them tangram pieces, which are different geometric shapes. So I'm going to ask you to just take a minute or 2 to think about the question that the teacher will be asking the students. Who can describe a rectangle? If you're sitting next to somebody, share a description with the person next to you, or just jot down a few descriptions for a rectangle. All right. And then I'm going to ask you to watch the video, focus on the students with 2 questions in mind. What mathematical practices did students use? I know I gave you that list a little bit ago. And how did students use language to communicate mathematical ideas? Listen carefully, watch Julian, read the subtitles, and I will also read the transcript right after the video clip.
Okay, today we are going to have a very special lesson in which, boy, you're really going to have to listen. You're going to put on your best listening ears, because I'm only going to speak English. Speak anything else, only English. Let's see how much we remembered from Monday. Hold up your rectangle high as you can. Okay, good. Now, who can describe a rectangle for me? Eric, can you describe it? Can you tell me about it?
A rectangle has 2 short sides and 2 long sides.
2 short sides and 2 long sides. Can somebody tell me something else about this rectangle? If somebody didn't know what it looked like, how would you say it?
Parallel.
It's parallel. Very interesting word. What does parallel mean?
Parallel.
Wow, that's a pretty interesting word, isn't it? Parallel. Can you describe what that is?
Never get together. No. They never get together.
Okay, what never gets together?
The parallel. When they go higher. They never get together. Yeah.
Interesting, isn't it? Very interesting. So that means if it's a rectangle, then the sides will never meet. Those sides will be parallel. Good word. Excellent word.
All right. So the teacher starts out by saying, today we're going to have a very special lesson in which you really are going to have to listen. You're going to put on your best listening ears, because I'm only going to speak in English, nothing else in English. Let's see how much we remember from Monday. Hold up your rectangles high as you can. Good. Now, who can describe a rectangle? Eric, can you describe it? What can you tell me about it? And again, what you're looking for here are, do you hear or see math practices, and how are students using language to communicate mathematically? A rectangle has 2 short sides and 2 long sides. 2 short sides and 2 long sides. Can somebody tell me something else about this rectangle? Julian says, paralela, and holds up a rectangle, the voice trailing off. It's parallel. Very interesting word, parallel. Wow, pretty interesting word, isn't it? Parallel. Can you describe what that is? Julian, never get together. They never get together. Runs a finger over the top side of the rectangle. What never gets together? Julian says the paralela, when they go higher, they never get together. And he's running two fingers parallel to each other, first along the top and the base of the rectangle, and then continues along those lines. And Antonio chimes in, and the teacher says, very interesting. The rectangle then has sides that will never meet. Those sides will be parallel. So I want you to notice, how did Julian describe a rectangle? So students were grappling with the definitions of quadrilaterals, but also with the concept of parallelism. So one important aspect of parallelism is that one needs to imagine, hypothesize, or predict what's going to happen to the two line segments if they're extended indefinitely. Although two line segments may not meet here and now, what matters when deciding if two lines are parallel or not is whether the imagined lines would ever meet. So let's start with, so what's the mathematical concept? It might be easier to see that by referring to a textbook definition for that concept. Here is a definition from a textbook. Straight lines in a plane which have no common point no matter how far they're extended. But this is not how we can expect students to describe parallel lines. That is not the point of what we want them to be doing when they're communicating mathematically, and this is not an appropriate expectation. So the first recommendation is to use the academic literacy and mathematics framing to focus on math practices, not on language as words, vocabulary, or formal definitions. Why is that important? Shifting from language as vocabulary or single words or formal definitions places an overemphasis on correct vocabulary and formal language. That limits the linguistic resources for learning or teaching math with understanding. And it also precludes students from participating in those valued mathematical practices. Now, it may be a challenge to hear math practices. For example, the emerging language and the ideas might be imperfect. So if we look at Julian's utterances, they may be difficult to hear or interpret. He hesitated when he said paralela. He may have been mixing English and Spanish. He added a to paralela instead of parallel and pronounced it in Spanish. And then a singular word, paralela, was followed by the plural when they go higher. But that's not what we want to focus on. Instead of focusing on what is not perfect, what is imperfect, or what isn't precise, what we want to focus on is on hearing math practices. So one question that people always ask is, so what was the hesitation? Was it due to like he didn't know how to pronounce the words, he didn't have the right word choice, or was it that the math idea? It is impossible to answer that question, certainly in the moment of teaching and even when analyzing a videotape. Instead, our job using the academic literacy and mathematics framework is to notice that Julian accurately described a property of parallel lines. Focusing on the math practices instead of formal vocabulary means that it's more important to listen for student math practices and to look at the meaning of the whole utterance. It's less important to focus on single words or formal vocabulary. So what math practices did Julian use? I see at least three: abstracting, generalizing, and imagining. He was describing an abstract property of parallel lines and making a generalization that parallel lines will never meet. He was imagining what happens when the parallel sides of a rectangle are extended. So if we see language as only vocabulary, we miss Julian's use of mathematical practices. I want to say a little bit about a math practice that comes partly from the Common Core, but it's also something that we tend to associate with mathematics, is attending to precision. And I want to give you some options for thinking about attending to precision is not precision in using vocabulary. And my favorite example comes from a statement that you might hear students in elementary school saying something like, multiplication makes the result bigger. So when I hear that, or a teacher hears that, or an analyst hears that, One teacher might say, attending to precision means that I want the students to say the precise word product instead of result, right? Because this is multiplication and the result, the precise word would be product. Another teacher would ask, when does multiplication make the result bigger? So by asking that question, this is precision, this is the practice of making claims precise. Not the precise word, but by saying, when does multiplication make the result bigger? We can start to ask, so is it when you're multiplying by a whole number? What about when you're multiplying by a number less than 1? And then you can get into what we absolutely love in mathematics, special cases. What happens when you multiply by 0? What happens when you multiply by 1? So again, the point of this example is that attending to precision is not fundamentally about the precise word. It's very important to engage students in the practice of making claims more precise. The second recommendation is to treat everyday and home discourses as resources, not obstacles. Why is this important? Because they're resources for communicating mathematical reasoning. What linguistic resources did Julian use to communicate his mathematical ideas? Well, he used everyday expressions, go higher and get together. And these were resources, not obstacles. Those are colloquial expressions instead of the more formal terms extended or even meet. So he was using hybrid linguistic resources and drawing on both everyday and academic registers. He did not use technical phrases, but an everyday phrase with mathematical meaning. Again, both of the registers, everyday and academic, they're not opposites, they're not at odds with each other. They both provide resources in the classroom. The discussion was mathematical, not because it involved technical math terms, but because it involved math concepts and math practices. What was the teacher doing? So a couple of things. Building on student resources, when Julian said paralela, the teacher repeated it, parallel, and built on that response by saying, can you describe what that is? Asking for clarification and explanation. Can you describe what that is? And then in another turn, when Julian said they never get together, he made that move that I described earlier. What never gets together? Asking Julian to make his claim more precise. And he rephrased student statements using more formal words and ways of talking. But again, the example, they never get together, by asking what never gets together is making the claim more precise. We can also look at how he rephrased the student claim. If we look at line 8, Julian says the paralela, they never get together. In line 10, the teacher says, which should be line 9. I just realized that numbering is off. That's okay. The rectangle then has sides that will never meet. So rephrasing Julian's never get together with will never meet, which is more formal. And then also bringing in the even more formal, those sides will be parallel. So to summarize, what did the teacher do? The teacher built on a student contribution. He supported the mathematical practice, attend to the precision of a claim. And he also provided more formal words like extended and meet. So the two recommendations for supporting English learners in math classrooms: using the academic literacy in mathematics framing to first focus on math practices, not language as single words or vocabulary. The second recommendation is to treat everyday and home discourses as resources, not obstacles, and they work together. They're not in opposition to each other. How can teachers support academic literacy in mathematics? First, it can provide opportunities for using the 3 components: the cognitive component, reasoning, thinking, conceptual understanding, metacognition, plus mathematical practices and discourses. Another thing that teachers can do to support academic literacy in mathematics for English learners is to create participation structures and norms that encourage student participation in math practices. And lastly, to use a complex view of mathematical discourses that involves using hybrid resources, both everyday and formal. So I'm going to mention these are a couple of articles using the academic literacy and mathematics framework. The original article is from 2015 in the Journal of Mathematical Behavior. And then there's another article from 2015, Scaffolding Mathematical Practices, that uses this excerpt. And there are two further articles based on this lesson, supporting the participation of English language learners in math discussions, and examining mathematical discourse practices. There's also, you can find those on my webpage. They'll also be available in the resource room. And there's also a piece called Mathematics, the Common Core and Language, which should still be available on the website for understanding language at ell.stanford.edu. Thank you so much. Hello, everybody. We have a few minutes for questions. And what I'm going to do is read your questions and then answer them. What professional development do you recommend to instill these strategies in our teachers' everyday instruction? Are there any teacher-friendly resources? Great question. Thank you. As you know, the best professional development is something that goes on for more than one day, over a long period of time. So something that goes on for a year or longer. It also should be based on teachers' own needs and what they're interested in. And it also should relate to the curriculum materials that they're actually using. So that's in general, that is the kind of professional development that works to help teachers improve their students' achievement and competence in mathematics. Teacher-friendly resources specifically for supporting language. There are these things called the math language routines, and they appear in a couple of places. One of them is in illustrated math. They were used in many of those lessons ahead of time, but you can also add the math language routines and learn to work with those as a group, again, doing lesson study, working with the lessons that you have and adding math language routines. And let's see, there should be a reference to math language routines. I'm going to spell the name of where I would look for that. It's Zwiers, Z-W-I-E-R-S. They're appearing in many different places. And again, those are the most useful resources for strategies. There are also some materials by New York City Department of Education. And the name to search for there, the last name is Zahner, Z-A-H-N-E-R. And again, they're materials from the New York City Department of Education. Anybody else have a question or a comment? Is anybody wondering, so what do you do with vocabulary? And what do we not want to do with vocabulary? I'm going to read a comment. Given that state assessments continue to require normative mathematical language, what I was calling formal mathematical language, to what extent should insistence on that language continue to be part of instructional practice? So this is the dilemma of teaching, is that we both need to start where students are and also help them move along. Not only for state assessments, right? But at some point, we would like them to have the choice to choose to participate in mathematical discussions where they use more formal mathematical language. The issue is thinking about a trajectory, right? Where are they? Where do they start? How do we build on what makes sense to them already? And then it takes time to learn to use language with meaning. And again, whether it's mathematical language or other kinds of language, I'm sure you had the experience of using a word for the first time in a foreign language and just saying it without a lot of grounding and meaning. So let's think about over multiple lessons and perhaps multiple years, if you start to introduce the word function, which is what I study, early on, let's say in the 8th grade, you know that students will be developing a deeper and deeper sense of the meaning of functions. Are they linear? Are they quadratic? What kind are they? When do I have it? Again, that takes years. So what I'm asking for is a developmental view of how students learn the meaning of mathematical language. Other questions? Vocabularies, do's and don'ts. There's something out there that we all think is good to do. I did it in my dissertation. I did it when I taught, which is pre-teaching vocabulary. The more that I read, I'm not a vocabulary expert, but the more that I read what vocabulary experts tell us is that's really not an effective way to learn vocabulary. Again, if you think about how you might have learned a foreign language, telling you what something means in and out, comes in one ear and out the other. Whereas what vocabulary experts tell us is we need to use words, make sense of them, do something, have an activity that has a goal with those words. If you use the word function just telling me, I love the definitions. I work with math, right? I love the definitions, but memorizing the definitions, whether it's in a textbook, on the board, wherever, coming out of somebody's mouth, is not how I develop meaning for the word function. The way I develop meaning for it is working with functions, again, over extended periods of time, where I'm actually making sense of what a function is and how functions work. So that's the short version of vocabulary do's and don'ts. Cognates. Absolutely, particularly for many of the Spanish cognates that are related to the Latin words that we use in English. And again, I hope that's enough tier 1 and tier 2. And yes, I'm actually not an expert in vocabulary. So when I think about teaching, tier 1 and tier 2 may not be the ways that I think about vocabulary. And strategic use of cognates can be very helpful. I'm going to go beyond cognates and say this. Students either at home or with their peers or in a math class in Spanish have done much more than learn the cognates. What they've done is they've also learned how to talk about mathematics. So we've got 30 seconds, and I'm glad that I got to say that. They also have learned other things besides the words in Spanish that we can build on. Thank you so much, and I'm not good at counting 30 seconds. If you have other questions or comments, I believe my email is somewhere. If you can spell my last name, you can Google it. And also, I think my email should be somewhere in the session. And by my clock, it is now 12:10. So thank you. Enjoy the rest of the summit.